Across the cold frontier of interstellar night, long before astronomers knew its name or plotted its course, an object drifted through the deep between stars. It slipped silently through the Milky Way's unlit corridors, older than our oceans, older than the Earth itself, older perhaps than the Sun, whose gravity would one day seize it for a momentary encounter. It carried no message, no intention, no warmth, only the ancient memory of a world long vanished, sealed inside ice and dust that had endured the slow violence of cosmic time. And then, without warning, it appeared at the edge of this human sight. A single line of numbers in a telescope's data stream, a speck moving against the familiar background of stars, a visitor whose trajectory did not belong to this solar system. Interstellar object. The phrase alone carries the weight of the unknown. Humanity has learned to read the sky with confidence, predicting orbits, mapping motions, naming patterns. But sometimes a stranger arrives with a different story, tearing through the quiet patterns that civilizations once assumed were permanent. And when it does, the sky becomes something ancient again, as if the universe momentarily remembers its wilder past. This one moved quickly, too quickly, a raw unbound speed unsoftened by the long companionship of planets or the gentle tug of a parent star, its path sliced not in the circle of our ecliptic but at a profound angle, as though it had come from somewhere immeasurable and was destined for somewhere beyond imagination. Its arrival was not an approach, it was an intrusion, a reminder that the cosmos is less a home than a crossroads. Later we would call it 3II, Atlas, the third interstellar object ever found. 3I marking its place in a lineage of visitors that began only with the last decade, Atlas honouring the survey system that caught its faint reflection before it vanished into the glare of our sun. But names came later. In the beginning there was only the astonishment of a new dot on a screen, too faint, too fast, too independent. And even then the mystery began to unfurl, because as this object came closer its appearance shifted. What should have been a crisp point of light softened into a hazy sphere, a cloud, a coma, as if the object were waking up under the touch of our star, shedding something ancient, something frozen, something fragile. Yet what it shed, and the proportions in which it shed it, did not match anything easily recognizable. It looked like a comet, behaved like a comet, and yet refused to fully belong to the definition. Scientists understood the strangeness instantly. If it was truly interstellar, then its ices were formed in a different sun's infancy. Its metals were shaped in a different nebula's chemistry. Its motion carried the gravitational scars of encounters older than Earth's iron core. To witness it was to peer into another solar system's geological past, preserved by the deep freeze of wandering between stars. But to witness it, humanity had only seconds, cosmically speaking. For 3 Atlas was not merely passing through, it was racing. A single swing through the sun's domain, a single curve, and then back into the void it would go. No return, no second orbit, no lingering. What is a mystery that cannot be revisited? What is a question that passes so quickly that science must chase it with every telescope, every instrument, every ounce of curiosity it possesses? Such is the drama of an interstellar visitor. It reminds us of our cosmic fragility, not in the sense of danger, but in the fleeting nature of opportunities to understand. The universe offers windows not in decades, but in moments. And those who look must look quickly. When 3I Atlas entered the solar system, the world below was busy with its own concerns. Politics, economies, the churn of human history. Yet above all of it, this intruder from the dark carried a stillness that seemed almost philosophical. It crossed the solar boundary as if gliding over the threshold of a quiet cathedral. It illuminated nothing more than a dust tail. And yet, by its mere presence, it invited questions that humanity has asked since the first fireside nights. What lies beyond our star? How many worlds have risen and fallen in the ancient black? How many fragments of forgotten suns wander between the galaxies? And deeper still, what does it mean to exist in a cosmos where even the smallest travellers have stories older than human language? Astronomers felt the shift immediately. Not fear, although some whispers in the public imagination would soon drift in that direction. What they felt was something closer to awe. A phenomenon that follows no familiar rule, expands the mind simply by existing. It breaks the comfortable assumption that our neighbourhood is insulated, predictable, known. And in that break, curiosity floods in. Far from the surface of Earth, orbiters, rovers and telescopes lay in wait, some decades old, some newly awakened, some not even scheduled to observe such an object. And as 3 Atlas moved toward the inner solar system, those instruments began turning their gaze. Each one positioned at a different vantage point captured a different texture, a different wavelength, a different whisper of information. But before the first images reached the public, before the instruments synchronized, before scientists could even compare early data, there was only this: a traveler from another sun drifting toward ours. Not a threat, not a message. Simply a fragment of the galaxy's memory offered to us for a brief, fragile moment. A moment that demanded attention. A moment that invited wonder. A moment where the universe seemed to say, look closely. Something ancient passes through your sky tonight. Long before the world argued about rumours or past live streams, there was a quiet night in the Chilean mountains, a night like thousands before it, when the sky was surveyed not by human eyes, but by a machine built to catch what the human mind was never meant to notice. The Atlas Survey Telescope, funded by NASA, yet operated with a routine rhythm swept across its assigned strip of sky. Its purpose was unglamorous, but essential: search for objects that move. Search for things that do not belong to the fixed tapestry of stars. Search for anything that might one day threaten Earth. It was during this steady work, this endless scanning of the heavens, that the first anomaly appeared. A point of light shifted where no point should move. A faint glimmer, barely distinguishable from noise, betrayed a subtle displacement. In the earliest frames, it looked like nothing at all. A pixel or two, an almost forgotten dot drifting sideways across the starfield. The system flagged it automatically. The human operator reviewed it manually. Both reached the same silent conclusion: something was there. At first no one knew its significance. Discoveries rarely arrive with fanfare, they slip in like whispers. What mattered was that the object moved at all, because anything that moves can be studied: its speed, its direction, its brightness, its intent, however unintentional. The operator, performing the same protocol used for asteroids and comets, plotted successive images, watching its position shift from night to night. And within hours, something astonishing became clear. Its trajectory did not curve like the familiar paths of solar system bodies. It plunged inward along a line so steep, so sharp, that it seemed to slice across the geometry of the planets. It was not orbiting the sun. It was approaching it only once, only briefly, before its speed would carry it out again. This object was not gravitationally bound to our star. The operator sent the alert to the Minor Planet Center. Coordinates, timestamps, motion vectors. And in the data that followed, the evidence strengthened. It was hyperbolic. Its eccentricity was greater than 1. Only 2 known visitors had ever announced such origins before: Oumuamua in 2017 and 2I/Borisov in 2019. And now, for the 3rd time in human history, the cosmos had sent another traveller into the realm of our star. Within hours, astronomers around the world reoriented their telescopes. The object was faint, still distant, still hiding in the dim borderlands beyond Mars's orbit. But its speed was undeniable. Initial estimates placed it near 58 kilometers per second, faster than any comet forged in our sun's cradle. Its angle of approach hinted at an origin not within the thin disk of the Milky Way, but potentially from a population of older stars, its motion a fingerprint of a very ancient birthplace. The discovery spread quickly through scientific channels. Emails fired between observatories. Orbit determination algorithms ran in parallel. Predictions sharpened. The object first noted on July 1, 2025 rapidly became the focus of intense scrutiny. In the halls of NASA's Goddard Space Flight Center, researchers gathered around screens not yet prepared for public release, tracing an interstellar visitor threading its way toward the sun. But as the data solidified, the moment of discovery took on a new dimension, because alongside the excitement was realization this object could be studied more closely than any interstellar object before it. Unlike Oumuamua, which was discovered on its way out, and Borisov, which was observed from only a handful of Earth-based angles, 3Y Atlas would pass a location rich with robotic observers: Mars, orbiters, rovers, satellites, a distributed armada of scientific instruments positioned throughout the inner solar system. The Discovery team understood instantly what this meant. For the first time in history, a visitor from another star would be observed simultaneously by telescopes around Earth and by spacecraft scattered across millions of miles. And as its trajectory placed it behind the sun from Earth's perspective, those spacecraft on Mars's side would become essential eyes, catching data Earth could not. The discovery had opened a window, and the scientific world knew it had to move fast. As the Atlas team prepared their official publication notes, other groups confirmed the detection. Images from the Catalina Sky Survey, observations from Pan stars, then small bursts of data from amateur astronomers who, upon hearing whispers of a new object, pointed their smaller telescopes into the void. Even among these modest instruments, the object's motion was unmistakable. It was too swift, too determined, too alien to the orbital choreography of the planets. Who discovered it first? Technically, Atlas caught the initial frames. But discovery in the scientific sense is not a moment, it is a consensus. A collective affirmation that what has been seen is real, measurable, and extraordinary. And so as the news circulated, the story settled. Atlas discovered the third interstellar object ever detected, a stray fragment of a distant solar system now wandering through ours. It was a testament to the quiet diligence of astronomers who watch the sky not for glory but for truth. In the early hours of its identification, before speculation filled the digital world, the object had no mystique, no mythology, no rumours attached to it. It was simply an unexpected arrival, a celestial wanderer carrying the unspoken history of another star. A piece of frozen time. Yet even then, in its untouched state, the seeds of mystery were already growing. For the first images revealed a halo, small, faint, unmistakable. A coma forming earlier than many expected, shedding gases in proportions that raise quiet questions among scientists. Questions about composition, about chemistry, about origins so distant they might predate the solar system itself. This was not merely a visitor. It was a witness, a remnant, a survivor of processes older than Earth's continents. And on that night, when the first observations were logged and the first coordinates sent, astronomy was given a gift that would unfold slowly, layer by layer, as 3 Atlas descended toward the sun's warmth. A discovery not of danger but of perspective. A discovery that would soon ignite fascination throughout the world, not because it threatened humanity, but because it offered, however briefly, a glimpse into a chapter of the universe long forgotten. Long before the official briefings, the calibrated images, or the meticulously worded scientific statements, something else began to take shape. An invisible atmosphere surrounding 3 high Atlas that had nothing to do with dust or gas. It was the atmosphere of human imagination. The object had barely been confirmed when the world beyond observatories seized upon its existence, and in the vacuum left by silence during the government shutdown, speculation spread with a speed rivaling the object itself. It began as modern mysteries often do, with a simple question whispered across forums and shared through millions of screens. What if this is not a comet? For many, the idea of an interstellar object was already extraordinary. The universe rarely sends its artifacts into the inner solar system, and rarer still are we positioned to observe them. Oumuamua had sparked global intrigue. Borisov had rekindled it. And now, with a third visitor arriving unexpectedly, and shrouded in the limitations of timing, people felt the familiar pull of wonder and suspicion. Why now? Why here? Why this trajectory? In the absence of answers, speculation thrives. Rumours took flight not because the object looked unnatural, but because the context surrounding it did. The shutdown had silenced NASA at the very moment the object became interesting. Public statements were delayed. Data appeared in fragmented glimpses. For those watching from afar, the timing felt dramatic, almost scripted, and in that vacuum narratives blossomed. Some claimed the coma looked too round, as if engineered. Others argued that its brightness variations suggested artificiality. Some pointed to the object's unusual carbon chemistry, even though those findings had not yet been released, insisting that imbalance meant intention. Still others, reaching back to Oumuamua's elongated silhouette and its own history of debate, insisted the lineage of interstellar objects was becoming suspiciously provocative. And beneath all these speculations was a single unspoken truth: humanity is rarely content with the ordinary, when the extraordinary seems almost close enough to touch. In digital spaces, the object became a canvas. People painted it with fears of incoming catastrophe, with hopes of extraterrestrial contact, with theories of lost probes, rogue technologies, or cosmic beacons. Every blurred pixel became a clue. Every vague press release became fuel. Some circulated amateur-processed images, sharpening noise into structure and structure into meaning. Others saw intention in the object's sunward tail, interpreting its unusual orientation as directional thrust rather than natural dust dynamics. But beneath the wildest theories was something quieter, more human, a collective desire for the universe to reveal a secret. When the livestream finally aired weeks later, the atmosphere was electric, not because people expected danger, but because they expected revelation. They wanted answers, or at least acknowledgement that the mystery was real. The scientists, of course, spoke calmly, grounding every observation in the language of physics and evidence. They reminded the world that comets, even interstellar ones, obey the natural laws we already know. They laughed gently at the more extreme claims, not dismissing curiosity, but reaffirming the discipline required to sift truth from imagination. Yet their very restraint created a new kind of tension. For some, scientific certainty was comforting, for others it felt evasive. The public latched onto small inconsistencies, slight hesitations in responses, the difficulty of estimating size, the early ambiguity about rotational signatures. They fixated on the rare chemistry carbon dioxide abundance, the nickel-to-iron ratio, the unfamiliar polarization patterns. They wondered why the best close-up images remained faint, why certain data required time for calibration, why observations from Mars were needed at all when Earth-based telescopes existed in abundance. And when scientists admitted openly honestly that 3I Atlas came from a population of stars older than our Sun, something shifted again. That sentence delivered with academic precision rippled outward through social imagination. Older than the Sun, older than our system, older than the worlds we have known. Suddenly the speculation took a more philosophical turn. If this fragment came from a solar system that no longer exists, then what became of that system? What stories might its dust hold? What forces ejected it from its home? Was it the survivor of a stellar death? A remnant of a shattered planetesimal? A frozen messenger carrying the fingerprint of ancient chemistry lost to time? And because human thought rarely separates wonder from myth, some wondered whether its journey was accidental at all. Even the simplest mysteries become magnified when framed by cosmic scale. A displaced comet becomes in the human mind a symbol of possibility, of fear, of meaning trying to emerge from the void. But what made the rumours surrounding 3 Atlas so persistent was not the object itself, nor even the evidence, but the tension between silence and anticipation. A global audience waited for clarity, and in the waiting imagination filled every gap. The scientists understood this dynamic. They knew that data takes time to downlink time, to calibrate time, to interpret responsibly. They also knew that the public seeks stories, not spectra, and 3I Atlas, with its interstellar origin, its strange brightness, its early coma, its unbound speed, and its arrival during a moment of national silence, offered a story too potent to ignore. Rumours did not grow because people mistrusted science. They grew because the universe had sent something rare, and for a brief moment it felt as though the cosmos itself was leaning closer. Scientists returned to the microphones when the shutdown lifted. They spoke plainly, they answered every question they could. They explained the nature of comets, the physics of dust, the chemistry of ice illuminated in infrared light. They offered the humility of uncertainty where needed, the reassurance of evidence where possible. But the fascination remained, not because the rumours were right, but because the human mind faced with a mystery older than the Earth instinctively reaches for meaning. For a moment, 3I Atlas was not merely a scientific object, it was a cultural mirror. It reflected our hunger for wonder, our fear of the unknown, our yearning to believe the universe still holds secrets waiting to be revealed. And though the rumours would fade as data sharpened, the mystery did not fade with them. For even after separating myth from measurement, the truth about 3I Atlas remained stranger and deeper than any speculation that preceded it. The first images of 3 Atlas arrived quietly, almost humbly raw frames caught by instruments designed not for spectacle but for truth. They came from telescopes orbiting high above Earth, from spacecraft drifting in the cold vacuum beyond Mars, from observatories positioned like sentinels across the solar system. Each image was unassuming at first, a faint blur, a diffuse glow, a point of light slightly too soft at the edges to be a star. But within that glow lay the first brushstrokes of astonishment. It looked like a comet. That was the first shock. Because it should not have looked like a comet. Not this quickly. Not at that distance. Not with a coma blooming so distinctly before the sun had even begun to warm its frozen surface. And certainly not with the particular profile that soon emerged. A teardrop haze, delicate yet strangely robust, forming earlier and brighter than models predicted for an object entering our system for the very first time. Hubble, the veteran sentinel of Earth's orbit, captured the earliest images sharp enough to reveal shape. At a distance of hundreds of millions of miles, the telescope's sensitive detectors caught what ground-based surveys couldn't. A developing coma shedding dust at a rate consistent with inner-system comets, despite the fact that this fragment had spent eons wandering far from any star. The shape was unmistakable, a white sphere of vaporized ices, a tail barely forming, not yet defined but present. light scattering through the dust, bending subtly under the pressure of solar photons. But inside that familiar image was something unsettling. The earliest calculations placed the nucleus somewhere between a few hundred meters and several kilometers across a range so wide that even seasoned astronomers hesitated. The object's brightness did not behave quite like the brightness of ordinary comets. It fluctuated subtly, its intensity modulated in a pattern that scientists struggled to interpret. Was it rotation? Was it dust? Was it composition? Something was different, though. No single instrument could yet prove what that difference meant. Then came the realization that startled even veteran comet specialists. The coma was not only strong, it was chemically unusual. As infrared instruments aboard James Webb and Sphere-X observed the object, the spectral signatures revealed something unexpected. A pronounced abundance of carbon dioxide relative to water. The ratio was unlike those typically observed in the icy bodies of our own solar system. It was as if the object's frozen interior held a blueprint of a very different kind of planetary nursery. A different star, a different nebula, a different time. The first shock was not that it was a comet. The shock was that it was a comet unlike those we understood. Meanwhile, Swift's ultraviolet detectors caught additional anomalies, gas emission patterns, that hinted at volatile elements erupting in unexpected proportions. As scientists compared notes across missions, they found themselves confronted with a portrait that refused simplification. Every new wavelength revealed a different face. Dust properties appeared peculiar. Polarization measurements suggested unusual grain structures. The early sunward-facing dust plume, rare among comets, challenged easy explanations. And although the nucleus remained unseen, hidden behind its halo of vapor and light, its influence radiated through every observation. This was an object forged in an environment that no human instrument had ever studied directly. The scientific shock became formal the moment multi-instrument comparisons confirmed that this was not merely an interstellar object, but one bearing chemistry noticeably alien to our solar system's norms. Not alien in the sensational sense, but alien in the true cosmic sense, documenting a world that formed under conditions foreign to everything familiar. Scientists were in their own quiet way astonished. Because across billions of years and trillions of miles, this fragment had carried its primordial signature intact. The shock also deepened when Hubble refined its orbital data. The object's speed, a blistering tens of kilometers per second, combined with its steep angle of entry, pointed toward origins not in the gentle spiral of the Milky Way's disk, but possibly in one of the galaxy's older stellar populations. Regions where stars had long since exhausted their hydrogen. Regions far from the chemical comfort that produced our planets and oceans. To see an object like this was to stare into a memory older than Earth, older than Mars, older even than the Sun. A frozen survivor of time beyond our reckoning. And then came the very first images from Mars. The Mars Reconnaissance Orbiter, positioned almost ideally for the encounter, captured frames that seemed at least at first glance unimpressive. But they were history. The closest images ever taken of an interstellar object. Pixel by pixel, they revealed something profoundly humbling. Even at close range, the object refused to show its core. The nucleus was swallowed in its own halo, as if guarding the secrets of its birthplace. This was the true scientific shock, the realization that despite unprecedented coverage, an object could remain stubbornly elusive. It was not simply distant, it was inherently enigmatic. Not by design, by nature. The more the cosmos revealed, the more it concealed. The early images showed only a brightening fuzz, a ghostly sphere glowing in the reflected sunlight. Yet within that fuzz lay contradictions. A comet that behaved both familiarly and strangely. A visitor whose chemistry spoke of a long-dead sun. A trajectory too ancient to trace. A nucleus hidden behind the very light it produced. It was like trying to study a whisper while standing in a storm. And it reminded scientists of an unsettling truth: most of the universe is not only unknown, but unknowable. Not because we lack the tools, but because some mysteries simply will not stay still long enough to be understood. As 3i Atlas hurtled deeper into the solar system, its coma grew brighter, its tail lengthened, its chemistry became more intricate, and the mystery deepened not because the object defied physics, but because it made physics larger, wider, more complex than previously imagined. This was the moment when astronomy collectively paused, not in fear, but in awe. A fragment from another star had blossomed into light under our sun, revealing patterns older than our world and threatening to overturn assumptions about how icy bodies form across the galaxy. Above all else, the early images made one thing undeniable: we were looking at something profoundly ancient, profoundly distant, and profoundly rare. and it had only just begun to reveal itself. In the long arc of scientific history, moments of discovery often unfold with precision data flowing freely, instruments synchronized, researchers connected across continents. But when 3U Atlas entered the solar system, an unusual stillness settled over the institutions responsible for interpreting its arrival. A silence not born of secrecy but of circumstance. A government shutdown had swept across the United States, freezing formal communication from NASA. At the very moment this ancient traveller began to stir under the sun's faint heat. It was an uncanny alignment of cosmic timing and earthly interruption. For days the object brightened. Instruments turned toward it. Raw data streamed through deep space networks. Yet the public heard nothing. Images remained unprocessed, press offices, unmanned, social media quiet. And that quiet became fertile ground for imagination. In the absence of clarity, anticipation grew first as curiosity, then as expectancy, then gradually as tension. The silence of uncertainty has a sound all its own. It echoes through speculation, amplifies the unfamiliar, magnifies every unanswered question. While astronomers worked behind the scenes, some unpaid, some volunteering, some navigating the constraints of a shuttered government, people on Earth filled the void with their own interpretations. The object was approaching perihelion. Its speed was increasing. Amateur astronomers were detecting changes in brightness. And yet the institutions normally tasked with informing the world could only wait. Every passing day felt like a deeper descent into mystery. Rumours took root not because scientists withheld truths, but because nature revealed its secrets in whispers while official channels could not speak. Online individuals pored over orbital charts, brightness curves, and early detections. They compared 3I Atlas to Oumuamua and Borisov, constructing narratives that blended science with conjecture. The silence acted like a mirror reflecting not the object itself, but humanity's fascination with the unknown. Meanwhile, inside laboratories and mission operations centers, the atmosphere was very different. Even under the constraints of the shutdown, some essential scientific functions persisted. Spacecraft continued their programmed observations. Telemetry still flowed. The deep space network still carried signals between Earth and the fleets scattered across the solar system. Engineers and scientists monitored automated processes, ensuring nothing critical was lost. Every instrument capable of observing 3I Atlas did so, each collecting fragments of a larger truth soon to be assembled. But without the capacity to speak publicly, NASA had to watch as an interstellar phenomenon ignited global speculation in real time. It was not the first time science had entered a quiet period during a critical discovery. History is full of moments where instruments recorded data faster than institutions could interpret it. But 3I Atlas was different. It was rare, it was passing quickly, and it was behaving in ways that seemed both familiar and strange. The combination of interstellar origin and sudden public silence created a perfect storm of uncertainty. In the quiet, the object continued its passage. Its coma expanded. Jets began to appear faint but detectable at multiple wavelengths. Water and carbon dioxide sublimated into space, forming patterns that hinted at the chemical landscape unlike any comet born in the sun's cradle. Hydrogen emissions registered differently on Mars's orbiting instruments than they did from Earth's side. Every new dataset revealed asymmetries, dust geometries, early outgassing. And yet none of these findings could be publicly shared. The world waited. The cosmos did not. As the shutdown dragged on, anticipation tightened like a string. People wondered, had something been discovered that could not be explained? Was there a threat? Was there a revelation being prepared behind closed doors? The reality was far more mundane and far more poetic. Scientists were simply doing what they always did, observing, analyzing, questioning, while the machinery of governance slowed their ability to communicate. But silence reshapes perception. It turns natural phenomena into mysteries. It turns distance into drama. It turns a fragment of ancient ice into a symbol. The shutdown eventually lifted. Systems rebooted. Communications reopened. NASA prepared a live stream to address the mounting speculation. When the doors finally opened, scientists emerged, not with revelations of danger or wonder, but with data calm, precise, steady. They explained that the object was a comet. They reaffirmed that it posed no threat. They shared the early images. They described the chemical signatures, the observations from Webb, Hubble and Swift, the ultraviolet detections from MAVEN, the perspectives gathered from Lucy and Psyche. Yet the world listened with an intensity that surprised even those delivering the information. For weeks, the silence had transformed 3i Atlas into something more than a scientific object. It had become a vessel for imagination. And now, confronted with the quiet rigour of astronomy, people tried to reconcile the gap between expectation and explanation. The uncertainty had altered the narrative. Even straightforward facts felt infused with gravity. When scientists mentioned that the object likely originated from a star older than the Sun, a collective shiver ran through listeners, not because the idea was new, but because the silence before it had elevated every detail into something monumental. When they spoke of the unusual carbon dioxide ratio, audiences leaned in as if hearing the first lines of a cosmic confession. When they described the faint jets and sunward dust tail, people interpreted the words as hints of a deeper revelation, rather than natural expressions of cometary physics. Silence had changed the emotional temperature of the encounter, yet something subtle and profound occurred as scientists continued speaking. The calm in their voices dissolved the tension that had accumulated during the shutdown. Not through denial or dismissal, but through clarity, through the steady, unwavering cadence of expertise. They acknowledged uncertainties openly. They celebrated the object's mysteries rather than deflecting them. And in doing so, the silence that once fueled speculation transformed into something far more valuable. It became a reminder of how deeply humanity yearns for meaning in the cosmos. A reminder of how silence can shape wonder just as much as revelation. A reminder that the universe does not bend to our calendars, our structures, or our moments of political interruption. 3. I-Atlas arrived when it arrived. It revealed what it revealed, and the world received only fragments until the channels of communication reopened. But within that uncertainty was something quietly beautiful, the recognition that even our most advanced institutions remain humbled by timing, by circumstance, by the vast, untamable rhythms of the universe. The silence did not diminish the wonder of the discovery. If anything, it amplified it. For when the veil finally lifted and scientists shared what they had seen, the world listened not as an audience waiting for spectacle, but as participants in a cosmic moment aware that for a brief pause in human affairs, a fragment of another star had crossed the sun's light in perfect indifferent silence. The return of NASA's voice after the long quiet unfolded with the familiar ritual instruments data, and the steadying presence of telescopes that have watched the universe for decades. Among them, one sentinel stood as the first to pierce the haze surrounding 3i Atlas, the Hubble Space Telescope, a veteran observer whose unblinking eye has traced everything from nearby comets to galaxies born near the dawn of time. Its role in this unfolding mystery was not merely observational, it was foundational. It provided the first stable anchor against which all later measurements could be compared. When Hubble turned toward the interstellar object in early July 2025, the target was faint 277 million miles from Earth, a speck barely distinguishable from background noise. And yet within that faintness, Hubble saw something other instruments could not structure. A teardrop-shaped coma, a sharply defined brightening at the centre, a dust plume already beginning to stretch away, although not in the direction most comets align. These subtleties did not reveal the nucleus directly, but they illuminated its presence hidden compact yet energetically active beneath the haze. The scientific shock lay not in the brightness nor in the presence of the coma, but in the timing. Comets forged in our solar system typically show this level of activity after prolonged warming, after many visits to the Sun, after the depletion of their outermost volatile layers. But 3i Atlas had spent uncounted millennia in the deep freeze of interstellar space. Its ices should have been dormant, resistant, frozen into crystalline rigidity. And yet here it was shedding dust and gas in a manner consistent with ancient sun-tempered comets. Hubble's early data indicated a mass loss rate comparable to familiar comets like 67P/Churyumov-Gerasimenko or Hale-Bopp. The proportions matched, yet the object did not belong to the family from which such comparisons were drawn. It was like watching a relic speak a language it should not know. The structure of the coma hinted at activity patterns unlike those observed in typical solar system comets. Some jets appeared to be emerging before conventional thermal models predicted sublimation should occur. The dust grains reflected polarization signatures that challenged expectations. The coma exhibited gradients that suggested deeper layers, perhaps untouched for billions of years, were reacting immediately to the sun's touch. What disturbed astronomers was not the behavior itself, but what that behaviour implied that the internal composition of this object was chemically ancient in a way our system could not produce. As though the object carried the frozen memory of a star older, colder and chemically different from our Sun, Hubble refined its estimate of the nucleus size, though only by bracketing it in uncertainty. Somewhere between 400 metres and 5.5 kilometres in diameter. A vast range, a sobering one. The earliest analyses suggested that the nucleus might be smaller than the Comet implied, or perhaps more reflective, or perhaps structurally unique. But one feature remained consistent, unlike Oumuamua, which confounded observers with its elongated silhouette. 3I Atlas appeared remarkably round, a sphere of primordial ice, a shape forged not by erosion or impact, but by the slow, even accretion of dust in a long-gone protoplanetary disk. As the data accumulated, Hubble revealed another crucial piece of the puzzle: the object's orbit. The telescope's precise astrometry allowed scientists to trace its inbound trajectory, confirming beyond a reasonable doubt that the object was not gravitationally bound to the Sun, not now, not before, not ever. It was a true interstellar visitor on a hyperbolic escape path, symmetric enough to feel eerie yet natural enough to satisfy Newton-Einstein and every law-binding celestial motion. But within the orbital refinement was a surprise. The object arrived from a vector suggesting it belonged not to the gentle disk of the Milky Way's spiral arms, but to a population of stars with greater age dispersion stars that roam the galaxy with motions acquired over billions of years, regions where ancient suns are born, burn and fade, long before Earth's core cooled. The significance struck researchers quietly. 3I Atlas likely formed before Earth existed. When the object released dust into space, that dust was a messenger carrying the chemical fingerprint of a world long vanished. The CO₂-to-water ratio, later confirmed by James Webb, was already hinted at in Hubble's brightness variations. These measurements suggested that the object contained an excess of carbon dioxide ice far more than typical comets, originating in our Kuiper belt or Oort cloud. It hinted at a different formation environment entirely. Perhaps a colder nebula. Perhaps a star born in a region richer in carbon-bearing ices. Perhaps a solar system whose composition we have never encountered. But Hubble delivered one more shock, less scientific than emotional. It showed the object as a blur even at its best. A soft halo with no revealing silhouette. A nucleus invisible behind its own luminous cloak. To the world watching, the image was underwhelming. But to scientists it was profound. It meant the object's secrets were buried deeper than cameras could reach. It meant the true story lay not in its appearance, but in its chemistry. It meant this was a mystery that could not be resolved by a photograph. Instead, it required spectroscopy, multi-angle coverage, and long-term monitoring tools capable of reading not shape but origin. Viewed through Hubble's lens, 3I Atlas was not an object but a question. A question about the diversity of planetary birthplaces. A question about the fate of ancient solar systems. A question about how many worlds rise and fall before their remnants drift into the paths of younger stars. The roundness, the brightness fluctuations, the early coma, the carbon-rich signature, the hyperbolic trajectory. Taken together, they form the first true scientific shock this interstellar comet was familiar enough to understand, yet alien enough to challenge every model built from our solar system alone. Hubble had opened the doorway to a mystery deeper than distance or motion. It revealed an object that reflected the physics we know but whispered of histories we do not. And as other telescopes prepared to observe 3I, Atlas. More closely, the shock that began with Hubble became the fuel for the next phase of investigation. A growing awareness that the cosmos had not merely sent us a visitor but a relic from a time older than our Sun. James Webb turned its mirrors toward the interstellar traveller, the way a cathedral turns its stained glass windows toward the rising sun, not to illuminate the glass itself, but to reveal what light can whisper when filtered through something ancient. Webb was never built to chase comets. It was built to peer into the beginnings of galaxies, to find planets in the dim glow of their stars, to study light so old it reaches us as a trembling ghost. Yet in this moment the telescope became something else, entirely an archivist of interstellar chemistry, capturing the spectral fingerprints of a visitor older than memory. When Webb first observed 3I Atlas, the object was still distant enough that no human eye could have recognized it as anything more than a faint smudge. But Webb does not see with eyes. Webb reads vibration molecules singing under the sun's touch atoms, resonating as they warm ices unlocking from cosmic dormancy. Its instruments can separate light into languages that no ordinary telescope can translate, infrared signatures that whisper of origin, composition, and the long, cold journey between stars. The first spectra stunned scientists. A strong, unmistakable signature of carbon dioxide ice erupted from the data far stronger than expected, far greater in proportion than seen in typical comets of our solar system. And beneath that CO2 signal, another line emerged, the glint of water vapour, though in a ratio that defied expectations. Where solar system comets often release water as their dominant volatile 3-fran atlace exhaled carbon dioxide with a vigour that suggested an entirely different birthplace. It was as though Webb had opened a time capsule sealed in the darkness between suns. The spectra showed that the comet's surface was layered, ancient and unprocessed. No repeated visits to a parent star. No cycles of melting and refreezing that erase the past. The gases detected were primordial ice formed in a protoplanetary disk billions of years ago, never warmed, never changed. Webb had effectively glimpsed the chemical blueprint of another solar system's dawn. And the farther scientists looked into the data, the stranger it became. Embedded in the molecular lines were hints of radiation processing signatures that suggested the comet had drifted through regions of the galaxy, bathed in harsher cosmic rays than the environments that cradle our own Oort cloud. The ices seemed altered not by warmth, but by time, by exposure to the invisible tides of interstellar space. They bore the scars of centuries measured not in human lifetimes, but in revolutions of the Milky Way. Then came SPHEREx, the newly launched observatory with its panoramic infrared view of the sky. Together with Webb, it caught the comet in wavelengths that revealed more than chemistry, they revealed context. SPHEREx confirmed that the comet's molecular ratios were not shared by any well-documented object in our solar system. If similar objects exist around our Sun, they have either never entered the inner system or have evaporated beyond recognition. But 3 Atlas, untouched until now, revealed compositions reminiscent of star-forming regions different from the one that birthed the Earth. The fingerprints suggested a birthplace perhaps colder than our own nebula, richer in solid carbon dioxide, or shaped by a young star whose radiation sculpted its early chemistry differently than the gentle warmth of our Sun. Webb also revealed details about the dust particles shed by the comet. Their infrared signatures indicated larger grain sizes and unusual mineral compositions, hinting that the solids within 3Y Atlas may have formed under pressures or temperatures foreign to our models. Some grains appeared denser, others more porous, and their distribution suggested a nucleus with a strangely uniform structure, an ancient body, whose formation did not mirror the chaotic mixing seen in the early solar system. Every molecule, every grain of dust, every subtle dip in the spectral curve acted like a clue. Together they painted a portrait of a comet that was both instantly recognizable and profoundly alien. But the real revelation of Webb's observations was not simply what the comet contained, it was what it lacked. For all its vigour, 3 Atlas showed no signs of technological signatures, no anomalous metallic compounds, no thermal behaviour inconsistent with natural sublimation. This was not an engineered artifact, nor a probe, nor a vessel. It was a natural object. But natural did not mean ordinary. It meant something deeper. A relic of cosmic evolution, a shard of planetary formation, preserved across unfathomable spans of time. And in that preservation was its gift. Webb's infrared gaze allowed humanity to examine for the first time the chemistry of a solar system that disappeared long before ours formed. Its star may have grown old, dimmed, died. Its planets may have been torn apart, swallowed, or flung into darkness. But one piece survived this shard of ice and dust drifting through this galaxy until chance delivered it into our Sun's embrace. Scientists realized that 3 Atlas was not just a visitor, it was a fossil. A fossil not of bone or petrified wood, but of astrophysical history. The spectral lines became a message, not intentional but no less profound, carried across eons, a record of conditions that shaped worlds we will never see. The infrared whispers from Webb told a story that no visible light image could capture. They revealed the hidden architecture of interstellar creation, the chemical diversity of distant nebulae and the resilience of ices forged in the first breath of a long-dead star. For the first time in human history, we held in our detectors the molecular memory of another solar system, and the comet had only begun to speak. The deeper scientists peered into the spectral fingerprints of 3 Atlas. The clearer it became that this object was not simply unusual, it was chemically foreign. The coma surrounding it, blooming brighter each day as it fell toward the Sun, behaved like a veil of clues, a moving archive of molecules shaken loose from an interior untouched for billions of years. But the true strangeness emerged. not from the presence of familiar substances, carbon dioxide, water vapor, nickel iron, but from the ratios between them, ratios that defied the patterns imprinted into every comet born beneath our Sun. It began with the carbon dioxide. Webb's early spectra had detected an unusually strong CO₂ signature, but when additional instruments Sphere-X, Hubble, Swift, and later MAVEN converged their readings, they revealed something unprecedented. The CO₂ to water ratio in 3 in Atlas was not merely high, it was disproportionately high, far beyond the envelopes of variation seen in our comets. In our solar system, even in the coldest regions of the Kuiper Belt, water ice remains the dominant volatile. It sublimates first loudly and predictably as comets awaken near the Sun. Carbon dioxide follows dancing outward from deeper layers. But 3I Atlas obeyed none of these expectations. The early coma suggested that carbon dioxide was erupting with unusual force, far outpacing the water vapor that should have dominated its outgassing. The implications rippled through comet science. Either 3I Atlas, formed in an environment colder than any found in the Sun's protoplanetary disk, or the star that birthed it, possessed a chemical composition fundamentally different from the Sun's. Both possibilities pointed to something extraordinary. The comet carried the memory of a different solar system sculpted by conditions the human species had never encountered. Meanwhile, mineral signatures from the dust told an equally puzzling story. Ground-based polarization measurements revealed scattering behaviors rarely seen in ordinary comets. When light reflects off dust, it carries information about grain size, shape, and structure. 3. I Atlas returned polarization patterns suggesting either unusually large grains or grains coated in materials foreign to our system's typical comets. Some grains reflected light, as though they had survived intense radiation environments regions with cosmic ray fluxes far higher than what permeates the Sun's protective bubble. The grain size distribution was bizarre as well. Dust models indicated a surprising abundance of intermediate-sized grains, neither the fine powders typical of solar system comets nor the coarse conglomerates associated with repeated heating cycles. This hinted that the comet's dust had never been reprocessed or melted. It had never fallen inward toward a star, never undergone thermal alteration. The dust was in every sense pristine. Then there was the nickel and iron. Comets in our system release these metals when solar radiation breaks apart dust grains. The ratio of nickel to iron is usually predictable, reflecting the proportions in which these metals formed inside ancient supernovae ratios that hold steady across most solar system bodies. But 3I Atlas violated this expectation, emitting more nickel relative to iron than is typical. The deviation was small in absolute terms, but large in meaning. It hinted at a stellar birthplace where supernova enrichment had followed a different trajectory. Perhaps an older star population, perhaps a region of the galaxy with a distinct chemical profile. Taken together, the CO₂ abundance dust scattering anomalies and metallic ratios pointed toward a truth both breathtaking and melancholic. 3I Atlas came from a world that may no longer exist. Its chemistry resembled not the solar system's vibrant youth, but the chemical signatures of ancient stellar populations, stars with lower metallicity, older ages, and colder natal environments. Regions where planets may have formed differently, where ice is condensed in subtly foreign patterns, where protoplanetary disks spun under temperatures and pressures unlike those that shaped Earth. Astronomers began constructing models of possible birthplaces. Some pointed toward older open clusters whose stars have long since drifted apart, others toward the thick disk of the Milky Way home to stars with motions unlike the Sun's calm orbit. Still others suggested that the object might originate from a system disrupted by gravitational interactions, perhaps a passing star, perhaps a dying one. Each model carried its own poetry. If the comet came from an ancient disk, its journey might have begun in a star-forming region 8 or 10 billion years old, older than the Sun by half the age of the galaxy. If it came from a disrupted system, it might be the last remnant of planets torn apart by stellar tides, or scattered in violent encounters. And if it came from a star gone supernova, its composition might carry the chemical scars of the explosion itself. But the most sobering thought came from chemical modelling. The ratios within 3 Atlas cannot be produced by any known environment in our solar system. They can only be produced by a solar nebula with a fundamentally different temperature gradient. The implications stretched beyond astrophysics into planetary science, chemistry, and the study of habitability. If planetesimals in distant systems form with such different volatile compositions, then the diversity of exoplanets already enormous might be even broader than imagined. Worlds rich in carbon dioxide ices could give rise to atmospheres unlike any in our system. Cold super-Earths might have crusts rich in CO₂ frost rather than water. Organic chemistry might evolve along different pathways entirely. In other words, 3i Atlas was not merely a comet. It was the first physical sample, albeit one we could only observe remotely, of planetary formation in another solar system. Scientists had long speculated about the diversity of exoplanetary chemistry, but until now all evidence came from afar, tiny blips in starlight faint atmospheres glimpsed through transit spectroscopy measurements clouded by enormous uncertainty. 3i Atlas changed that forever. For the first time, humanity could observe the volatile chemistry, dust properties, and metallic content of an extrasolar planetesimal up close, illuminated by our Sun. One of the most striking results came from combining SphereX's broad spectral sweep with Webb's precision. The merged dataset revealed a subtle dip in reflectance at wavelengths associated with processed organic compounds, complex carbon chains that may have been irradiated over billions of years. These were not biosignatures, nor did they hint at life, but they did point to rich interstellar chemistry sculpted in the dark spaces between stars. In this way, 3i Atlas became more than a visitor. It became a cosmic historian. Its ices, layered like geological strata, held the remnants of physical conditions long extinct. Its dust, shaped by ancient cosmic rays, told of long wanderings through interstellar voids. Its composition traced the signature of a star whose life cycle had passed into obscurity. Everything the comet shed into space was a clue about somewhere else. A world unseen, a star forgotten, a history unwritten. The Comet's unearthly ratios were not just numbers. They were the chemical echoes of a vanished place. And as those ratios became clearer, the comet grew stranger, not because it defied physics, but because it expanded what physics had allowed humanity to imagine. Long before 3i Atlas ever brushed the outskirts of our solar system, long before it awakened, beneath the sun's distant warmth, it had already lived through a journey of extraordinary age. A journey that began in a cradle of light, now lost to the galaxy, a star system whose remnants may no longer shine, whose planets may long ago have cooled into darkness, whose history remains unrecorded, except for this one fragment of ice and dust. When astronomers looked at its trajectory, when they studied the strange compositions encoded in its coma, they realized they were not simply tracking a comet. They were retracing a ghost orbit through time. Its incoming velocity, slightly above 60 kilometers per second, was the first clue. Objects born within our solar system rarely exceed those speeds unless dramatically perturbed. But interstellar objects freed from the gravitational pull of a parent's adrift with the statistical motion of their stellar populations. And 3i Atlas drifted faster than most stars in the Sun's neighborhood. Its motion carried the signature of an older stellar generation, one whose members had been stirred over billions of years by galactic tides, supernova shock waves, and the slow churn of the Milky Way's disk. Its path through our solar system was steep slicing across the ecliptic at an angle reserved for things not shaped by our Sun. Even before the full orbital solution was refined, models showed that 3i Atlas had not originated from any known direction associated with local stellar associations. It was not a visitor from a nearby cluster, nor a traveller from one of the Sun's more youthful neighbours. Instead, it arrived from a direction where older stars dominate a portion of the sky, hosting populations that have wandered the galaxy several times since their birth. To trace its past, astronomers began a kind of cosmic archaeology. They ran integrations of its motion backward in time, not for centuries or millennia, but for millions of years, an exercise fraught with uncertainty. Because tiny gravitational nudges accumulate, cosmic rays alter trajectories subtly, and interactions with interstellar clouds can shift an object's course in ways mathematical precision cannot fully capture. Still, the models revealed broad patterns. Over tens of millions of years, the object's path scattered into a haze of possibilities, a widening cone that reached deep into the thick disk of the Milky Way, a region populated by stars that formed billions of years before the Sun ignited. This was the first profound realization 3i Atlas likely originated from a solar system far older than our own. Its strange chemistry supported this. The high carbon dioxide ratio, the nickel-enhanced dust, the unusual polarization patterns, all of these matched the environments expected in protoplanetary disks with colder temperatures, lower metallicity, and slower chemical evolution. These are signs of systems born in the early epochs of the galaxy when heavy elements were less abundant, and planetary formation followed pathways different from those that shaped Earth. If the object formed 4 or 5 billion years ago, it would already be older than Earth. But if it formed 8 or 10 billion years ago, as some chemical models suggested, it would belong to a time when the Milky Way was assembling itself from primordial clouds, when the galaxy was younger, rougher, and more chaotic. It might have been born around a red dwarf that has since burned itself into quiet stability, or around a sun-like star that has long since aged into a white dwarf shedding its planetary system in the process. It might even be a fragment of a world torn apart by gravitational encounters, a shard of a planetesimal belt disrupted when its star migrated through the galaxy, or brushed too closely past another stellar system. Every theory painted a different portrait, yet they shared a common theme. This object was a survivor of processes far older than anything in human history. The idea that 3I Atlas could be a relic from a dissolved solar system carried a strange emotional resonance. It suggested that the universe is full of abandoned histories, planetary systems that lived brief, brilliant lives before fading into obscurity. If so, then interstellar comets like 3I Atlas are not anomalies, but emissaries of forgotten worlds drifting archives of cosmic memory. Some researchers modelled the possibility that the comet's original home was destabilized by its star's evolution. As stars age, their gravitational reach changes. Their luminosity rises, their winds strengthen. When a star evolves into a red giant, it can fling cometary bodies outward, ejecting them into interstellar space. In this scenario, 3I Atlas could be a remnant expelled during a cataclysmic stellar transformation, an object that witnessed the death of its own sun before being cast out into the cold. Others favoured a quieter explanation, gentle erosion of the comet's orbit over hundreds of millions of years nudged by passing stars, until its trajectory finally broke free. In this version of its story, 3I Atlas spent most of its existence drifting silently through the galaxy, its ices freezing deeper and deeper, its surface sculpted by cosmic rays, until the moment it met our sun and awakened for the first time in billions of years. And yet even in their most ambitious models, scientists acknowledged that the comet's origin might never be pinpointed. The galaxy is too vast, too dynamic, too tangled with gravitational interplay. A single comet cannot preserve a precise map, but what it can preserve is something perhaps even more valuable, the chemical truth of its birthplace. That truth is written in its volatile ratios, its mineralogy, the pattern of outgassing that shaped its coma, the spectral lines captured by Webb and S-X. These details do not reveal coordinates, they reveal conditions, temperature, density, radiation environment, elemental abundance. In these clues, scientists glimpsed the story of a solar system so different from ours that its signature could not be mistaken. 3I Atlas was not just from another star, it was from another era, perhaps from another chapter in galactic evolution, perhaps from a time when the Milky Way was still sculpting itself, perhaps from a world whose planets cooled long before Earth was born. As it raced through our solar system, accelerating toward the dark beyond the sun, the comet carried within it the quiet weight of ages, a drifting witness to the birth and death of stars, a shard of a planetary system lost somewhere in the galaxy's ancient tides. Its journey reminded humanity not only of the vastness of space, but of the depth of time. The worlds that existed before us are countless. The worlds that will exist after us are unimaginable, and between them, drifting silently, lie the remnants. Sometimes they pass our way, sometimes they burn brightly enough for us to see, sometimes they whisper their story through light and dust. 3I Atlas was such a whisper, faint, fragile, and immeasurably old. Long before Earth had a clear view, long before the object's coma expanded into a luminous veil visible even to modest terrestrial instruments, Mars found itself in a uniquely fortunate position. By coincidence of orbital geometry, an accident of timing that could not have been engineered, even had humanity tried, Mars stood on the correct side of the Sun when 3I Atlas made its inward swing. Earth, positioned behind the Sun relative to the comet's path, was effectively blind during crucial days. But Mars, with its fleet of orbiters circling like iron satellites around a desolate world, had an unobstructed view. For the first time in human history, an interstellar visitor was observed not primarily from Earth but from another planet. As 3I Atlas approached perihelion, the Mars Reconnaissance Orbiter, MRO and MAVEN, two veterans with very different purposes turned their instruments toward the intruder, and what they saw offered a new layer of the mystery, a comet acting strangely in the light of a foreign sun. The ultraviolet signature. MAVEN's imaging ultraviolet spectrograph was not built for comets. It was built to study Mars's atmosphere, its hydrogen corona, its seasonal variations, its loss of gas to space. Yet when the spectrograph captured 3 Atlas, it revealed something extraordinary. In the raw ultraviolet frames, the comet did not appear as a tail or a cloud. It appeared as a compact sphere of hydrogen emission, separate and distinct from the hydrogen bleeding off Mars's own atmosphere. By separating the spectral lines according to Doppler shift according to speed, scientists could isolate 3 distinct sources: hydrogen from Mars, bright and stationary in MAVEN's reference frame; hydrogen from the interplanetary medium drifting slowly through the solar system; hydrogen from 3 Atlas moving at high velocity and confined to a tiny region of space. For the first time, a signature of water loss from an extrasolar object was observed not as a spectral curve, but as an image, a blob of ultraviolet light precisely where the comet lay. This revealed something profound. The comet was shedding water, but at a rate and in a structure that did not mimic ordinary solar system comets. Instead of forming a broad hydrogen cloud, 3 Atlas produced a more compact distribution, perhaps due to unusual dust properties, perhaps due to the balance between CO2 and water, or perhaps due to deeper structural differences in its ice layers. The sunward tail, but the true shock came from MRO's HIRIS-A camera, the same instrument that once revealed avalanches on Mars dust devils crawling across the red desert and the tracks of rovers wandering the plains. In its images, 3I Atlas did not display the typical antisolar tail, the elegant plume pointing away from the sun like a luminous banner. Instead, early frames showed a sunward-facing tail, a phenomenon observed in only a handful of comets throughout history. This was not an indicator of artificiality, nor of propulsion, nor of anything unnatural. It was a clue about dust grain behavior. Tiny particles so fine that solar radiation pressure should push them away were instead held close. Perhaps by electrostatic effects, perhaps by low mass, perhaps by a higher than usual abundance of ultrafine grains. In some models, such particles cling briefly in the sunward direction before being swept back into the traditional tail. But 3I Atlas exhibited the phenomenon with a clarity unusual for any comet and unprecedented for an interstellar one. For scientists, this was electrifying. A dust environment shaped not by our sun, but by another star's early environment. A fingerprint of a long-dead solar nebula, encoded in grain size and charge and structure. Mars is a front-row witness. For nearly a week, Mars became humanity's outpost, our cosmic lookout. While Earth was hidden, the red planet's robotic guardians watched the interstellar traveller drift past at a distance of tens of millions of miles, close by cosmic standards, impossibly distant by human ones. Every orbiter contributed something. MRO high-resolution visible imaging, MAVEN ultraviolet spectra and hydrogen mapping. Odyssey and Mars Express contextual imaging and infrared scans. Perseverance, though not aimed directly at the comet, recorded environmental data, altered subtly by dust scattering in the Martian sky. Mars became not just a vantage point, but a collaborator and extension of Earth's scientific vision. The chemical echo, MAVEN's data, when combined with Swift's and Webb's earlier detections, refined one of the most important measurements in cometary science, the water production rate. In ordinary comets, the water coma dominates by the time they reach this region of the solar system. But in 3 Atlas, carbon dioxide remained unusually strong, even near perihelion, hinting at a compositional structure that inverted the typical volatile layering found in solar system bodies. MAVEN detected hydrogen from water sublimation, but in amounts suggesting that beneath the CO₂-rich surface, the water ice either lay deeper, was more crystalline, or had been altered by cosmic rays over eons. This subtlety added weight to the hypothesis that the comet originated in a colder older disk, where CO2 froze readily, while water, less volatile, played a secondary role in early ice formation. A rare opportunity. Scientists knew how remarkable this was, a comet from another star passing close enough to Mars for detailed multi-wavelength observations. This was not just rare, it was unprecedented, and it may not happen again for centuries. In the images released later, the comet appeared almost modest. A white smudge, a handful of pixels, a fuzzy halo against a dark void. But behind those pixels lay the combined intelligence of 2 planets Earth watching through its fleets of telescopes. Mars catching what Earth could not see. The value of Mars' viewpoint was not in dramatic visuals, but in angles. Earth saw the comet obscured by the sun. Mars saw it illuminated. Different geometries, different dust scattering different spectral slopes. Together they allowed scientists to reconstruct a 3-dimensional picture of how the coma behaved, how the dust lifted, how the gases diffused, how the jets flared, how the sunlight sculpted the drifting grains of a long-dead solar system. A wordless witness. As the comet drifted past Mars, moving inward toward its brief encounter with the Sun, it left behind in the orbiter's detectors a trail of data finer than any photograph. It left a portrait written in ultraviolet dust polarization and gas dynamics, a portrait unlike anything ever recorded. It reminded humanity that mysteries do not require dramatic shapes or luminous tales to be profound. Sometimes they're found in the smallest deviations, the faintest asymmetries, clues that speak not of danger but of difference. Mars had been the closest witness to an emissary from another world, and in its silent orbit, it caught the whispers of an ancient system carried in sunlight across the void. 3i Atlas continued its journey inward, but the story it told around Mars, quiet, subtle ultraviolet, would become one of the key chapters in understanding where this traveller truly came from. Across the solar system, far from Mars and farther still from Earth, a fleet of spacecraft never designed to work together, never meant to form a single observing network, found themselves united by the passage of a visitor older than any world they orbited. No commander gave the order, no mission designer foresaw the need, but as 3i Atlas carved its trajectory through the inner solar system, instruments from a dozen distant machines turned their gaze upon it, forming a mosaic of perspectives unlike anything in the history of astronomy. This was not coincidence. It was opportunity seized by human curiosity, enabled by decades of engineering and shaped by the geometry of the moment. To understand the complexity of this effort, one must picture the solar system not as a diagram, but as a vast architectural structure of moving platforms. Each spacecraft, Lucy near Jupiter's orbit, Psyche in deep space, en route to a metal asteroid, SOHO, stationed between Earth and Sun, Parker Solar Probe. Orbiting in a furnace of plasma occupied a different vantage point, each seeing the same object from a different angle in a different light at a different moment. Together their observations formed a constellation of knowledge. Lucy the Trojan Scout. The Lucy spacecraft, on its long journey toward Jupiter's Trojan asteroids, found itself perfectly positioned to catch a distant backlit view of 3i Atlas. Lucy's LaLaurie camera, designed to resolve small bodies illuminated by the distant sun, captured one of the clearest large-scale shots of the comet's extended coma and early tail. What made Lucy's perspective invaluable was not image sharpness, but lighting geometry. The sun lay behind the comet from Lucy's viewpoint, highlighting dust structures invisible to Hubble and ground-based telescopes. The light scattered through the coma revealed gradients of particle size, coarse grains casting gentle halos, fine grains forming sharp edges. The tail, faint but present, extended slightly to the right of the nucleus, tracing the subtle push of radiation pressure. Lucy's photos, though pixelated, offered the first real clue that the comet's dust contained an unusual proportion of mid-sized grains, a finding later corroborated by polarization measurements. Psyche, the deep space witness. While Lucy viewed the comet from one direction, the Psyche spacecraft, still cruising toward the massive asteroid 16 Psyche, observed it from nearly the opposite side. Psyche's imager captured the comet as a dim, drifting ball of light across several hours. Stacking these frames produced a clearer composite, revealing a symmetric glow that contrasted with Lucy's asymmetrical backlit view. The symmetry in Psyche's frames suggested that some of the dust features seen by Lucy were angle-dependent, not intrinsic to the comet. This two-sided confirmation helped scientists rule out the possibility of unusual structural asymmetries in the nucleus itself. Psyche and Lucy, operating millions of miles apart, offered the first stereoscopic view of an interstellar object. SOHO, the Sun Watcher. Closer to the Sun, the joint ESA NASA SOHO observatory captured the comet using its chronographs cameras normally tasked with watching the solar wind, tracking coronal mass ejections, and identifying the thousands of sun-grazing comets that perish near the Sun each year. SOHO's observations of 3i Atlas were never guaranteed. The comet was expected to be too faint. But with stacked imaging techniques aligning and layering dozens of frames, SOHO revealed a faint but distinct point sweeping across its field, confirming the comet's trajectory, at a time when Earth-based telescopes were nearly blind due to solar glare. This detection demonstrated another truth: even an interstellar object moves according to the quiet laws of light and dust. Parker Solar Probe, the inner sentinel. In the oven of the Sun's corona, Parker Solar Probe flew closer to the star than any machine built by humanity. Its cameras, hardened against harsh radiation and blinding luminosity, caught several brief glimmers of 3i Atlas, fleeting streaks of brightness against the turbulent solar background. These glimpses were too faint for dramatic imagery, but they were priceless scientifically. Parker's vantage point allowed scientists to test whether the comet interacted with the solar wind differently from local comets. The answer was striking in its subtlety. 3 of Atlas produced a normal plasma signature, meaning its ions behaved exactly as expected when struck by the sun's charged particles. The cosmos, despite its diversity, adheres to universal rules. TESS and SWIFT, the multi-wavelength eyes. Even missions with unrelated purposes like the transiting exoplanet survey satellite TESS and the Swift Gamma Ray Observatory joined the watch. TESS, designed to monitor star brightness to find exoplanets, inadvertently captured the comet weeks before its official discovery, its sensitive detectors recording faint dimming patterns as the object passed through its wide-field view. Once the comet's trajectory was known, scientists combed TESS's archives and found these early frames. They showed 3-eye atelace before its coma awakened, giving rare insight into its dormant state. Swift contributed ultraviolet and X-ray readings detecting signatures of volatile release and the effects of solar wind charge exchange processes that transform raw cometary gases into glowing atoms visible in high-energy wavelengths. Sphere-X, the newcomer. The Sphere-X mission, launched only months before the comet's arrival, offered a broad-field infrared spectrum. Unlike Webb, with its surgical precision, Sphere-X provided sweeping coverage. This gave scientists a contextual backdrop for Webb's detailed chemical readings, confirming that the elevated carbon dioxide levels seen in 3Y Atlas were not artifacts of observation, but intrinsic to the object. A symphony of instruments. No single spacecraft revealed the comet's nature, but together they created a portrait. Lucy revealed grain scattering. Psyche provided structural symmetry. MRO and MAVEN gave ultraviolet and close-range geometry. Webb and Sphere-X decoded its chemistry. Hubble refined its orbit and brightness patterns. SOHO tracked it near the solar glare. TESS supplied pre-discovery data. Swift recorded high-energy emissions. Parker probed its plasma behavior. Each instrument offered one thread. Together they wove a tapestry. This was the first time in human history that nearly 20 spacecraft across the solar system cooperated scientifically, if not intentionally, to study a single interstellar visitor. The comet did not pass near planets intentionally. The spacecraft did not align themselves for an interstellar experiment, but for a brief moment the solar system became a natural observatory, every vantage point offering its own sliver of truth. From this distributed architecture of eyes emerged a deeper understanding not only of 3 Atlas, but of how science itself functions at the scale of worlds. The comet revealed itself not through proximity but through perspective, not through dramatic visuals but through the quiet accumulation of data from many places at once. This was the solar system speaking in harmony, and the traveller, this ancient fragment from a long-dead star, drifted through their collective gaze before vanishing toward the dark beyond Jupiter. By the time 3I Atlas reached the inner curve of its solar swing, scientists had amassed enough observations to begin probing one of the most revealing but also most subtle features of any comet: its motion. Not the broad, sweeping arc of its path through the sky, which was already known to be hyperbolic and unbound. Rather the tiny deviations, the delicate nudges and whispers of force that occur when a comet releases gas or dust. These effects, known as non-gravitational accelerations, offer a rare window into the interior of a comet, its structure, its activity, its rotation, its heating profile, even its porosity. For an interstellar object, the stakes were higher still. Its motion was not just a matter of orbital mechanics, its motion was a message. The rocket effect of ancient ice. Any comet, when warmed by the sun, sheds volatiles that escape into space like jets from a series of microscopic thrusters. Even a small outgassing event can subtly alter the comet's trajectory. The direction and magnitude of these deviations depend on the location of active vents, the shape of the nucleus, the distribution of ices, and the comet's rotation. In solar system comets, the pattern is familiar. Predictable accelerations aligned with known sublimation points, strongest near perihelion, fading as the comet recedes. For 3I Atlas, scientists expected something broadly similar, but what they found hinted at something different beneath the surface. Using precision astrometry from Hubble, Lucy Psyche ground-based telescopes, and Mars-based triangulation, the Jet Propulsion Laboratory confronted the object with mathematical rigor. Even after accounting for observational noise, solar radiation pressure, and measurement uncertainty, the comet's motion displayed subtle, persistent non-gravitational effects. They were not dramatic. They were not anomalous. They were not a sign of artificiality, but they were unusual. They aligned with typical comet behavior, but with one curious twist: the magnitude of the acceleration suggested vigorous outgassing, paired with a nucleus that was possibly smaller than its coma implied. This indicated either a nucleus with unusually efficient sublimation, or one rich in volatiles locked near the surface, or one with structural properties different from comets shaped by our Sun. Any of these would be consistent with a body formed in a colder older nebula, one that never experienced repeated meltdowns or perihelion passages. Rotation without signature. Ordinarily, rotational periods can be inferred from brightness variations, sunlight reflecting differently as a tumbling nucleus exposes facets of varying reflectivity. But for 3 Atlas, the nucleus was so deeply buried in its coma that no consistent periodic pattern emerged. This absence told scientists something unexpected. The nucleus might be nearly spherical, lacking the elongated silhouette that produces strong brightness cycles, or rotating slowly, or coated in dust so uniformly that rotational modulation was dampened, or releasing volatiles through distributed pores rather than single dramatic vents. In all scenarios, the implication was the same. The nucleus lacked the complex surface sculpting that repeated solar heating induces in solar system comets. It was in effect unweathered, a shape carved by its formation not by a lifetime of orbits, jets and the question of activity. As 3 Atlas neared perihelion brightness maps from ground-based telescopes and infrared models from Webb, suggested that the coma was not simply expanding uniformly. It showed faint structures, subtle enhancements consistent with jets. Jets are not explosions, they are regions where deeper ices reach sunlight and erupt as plumes. On Comet 67P, the Rosetta spacecraft saw hundreds of such bursts localized to specific fractures and pits. For 3I, at Aeolus without direct imaging of the nucleus jets could only be inferred indirectly, but the evidence was growing. Variations in dust distribution, localized brightness spikes, changes in gas emission ratios, slight directional asymmetries in the coma. These suggested that the interstellar object had not remained inert for all of its long voyage. Rather, it still retained internal structure zones of denser ice pockets, of less processed volatiles fractures that allowed outgassing to escape in irregular patterns. When the Mars Reconnaissance Orbiter captured a faint sunward-facing dust plume near perihelion, the theory of jets gained momentum. Jets can create momentary sunward puffs if they erupt from the side of the nucleus facing the star. Nothing explosive, nothing unnatural, simply the physics of sunlight meeting ancient ice. The resonant calm of natural motion. In the NASA briefing, scientists noted with care that the non-gravitational forces on 3I Atlas were consistent with those seen in comets from our own system. That is, they existed. They shifted the orbit slightly. They did not exceed expected magnitudes, and they obeyed the physical rulebook of sublimating ice. But the deeper truth understood quietly within the scientific community was that the pattern of these forces hinted at the comet's deeper story. It painted a picture of a nucleus likely smoother than 67P, more intact than Borisov, more typical in shape than Oumuamua, and structurally ancient but not brittle. This made 3R Atlas an extremely rare specimen, an interstellar comet that never broke apart despite billions of years of wandering, a traveller shaped by stars, not suns. When scientists reconstructed its inbound motion across millions of years, they found that the comet's accelerations aligned with what would be expected for an object drifting through cold interstellar regions, cosmic ray-rich environments, passes near other stars, and the gentle tides of galactic rotation. Everything in its motion whispered of antiquity. Its path had drifted through the galaxy like a leaf blown by long, slow winds, nudged by forces imperceptible on human timescales, but immense over billions of years. The comfort of ordinary physics. Perhaps the most poetic aspect of its motion was that it obeyed the same laws as every comet humanity has ever observed. The forces acting upon it were natural, quiet and familiar gravity, sunlight sublimation, dust dynamics. Even while its chemistry marked it as alien, its behavior was profoundly universal. It was a reminder that the universe is not chaotic beyond comprehension. Even a fragment from an ancient star system obeys the same cosmic grammar as a comet birthed in our own. The mystery, then, was not whether it defied physics. It was how physics had shaped it across epochs far older than Earth. 3. Atlas continued outward, its non-gravitational nudge fading as the sun's warmth diminished. The jets quieted. The dust production slowed. The nucleus retreated into its cloak of ancient ice. Its motion stabilized. Its story deepened. And scientists continuing their measurements realized that even the faint accelerations recorded in its path were chapters in a biography not written by humans but by the galaxy itself. In every great scientific mystery there comes a moment when the gathering of data, no matter how exquisite, inevitably gives way to interpretation. When measurements become stories, spectra become arguments, and a portrait assembled from the delicate filaments of observation must confront the harder question of meaning. For 3I Atlas, this moment arrived as the final wave of early observations settled into clarity. The comet had revealed its chemistry, its motion, its morphology, its dust, its volatile ratios. What remained was the deeper inquiry: what exactly is this object, and perhaps more importantly, what does it represent? This section, The Great Interpretations, was less about certainty than possibility. Interpretations are not guesses. They are the disciplined imagination of science grounded in evidence yet reaching toward truths that the instruments alone cannot express. 1. The ancient comet hypothesis. The most conservative interpretation, and the one most widely supported, held that 3I Atlas was simply what it appeared to be: an interstellar comet, forged in the protoplanetary disk of another star billions of years ago. Under this model, its unusual CO₂ to water ratio reflected the chemistry of its birthplace. Perhaps the star that birthed it radiated more strongly in its infancy, driving water inward and leaving carbon dioxide ice dominant in the outer regions. Or perhaps the temperature profile of that far-off nebula allowed CO₂ to condense earlier and deeper, embedding the comet's nucleus with an abundance rare in our system. This interpretation casts 3I Atlas as a pristine survivor from the earliest era of that star's formation, a messenger from a world that may no longer exist. Its dust composition, grain size distribution, and metallic ratios all supported this. Nothing about its behavior violated physics. Nothing suggested an engineered structure. Behaved like a comet, it sublimated like a comet, it drifted like a comet through the solar wind. If this was true, then 3I Atlas represented something profound, the first well-observed sample of planetary formation in another solar system, a cosmic fossil, a whisper from a galaxy's childhood carried across billions of years. 2. The disrupted system hypothesis. Others proposed a more dramatic but still natural explanation. In this framework, 3I Atlas formed in a young planetary system but was violently expelled either by a passing star or by gravitational chaos within its own system or by the death throes of its parent star. This idea found support in 2 key observations. Its inbound velocity exceeded that typical of stars in the Sun's neighbourhood. This hinted that the comet may have been ejected at unusually high speed, perhaps by stellar interaction or the collapse of a gas giant's orbit. Its ancient chemical ratios implied a birthplace in a system now long gone, a system that might have dissolved or migrated or aged into obscurity. Under this view, 3I Atlas was not just a messenger, it was a refugee, a displaced fragment of a violent past. 3. The rogue planetesimal hypothesis. There is a class of objects rare, subtle, and difficult to identify, known as rogue planetesimals. Fragments that drift between stars without having formed in the conventional manner within a stable disk. These bodies might form in isolation within turbulent molecular clouds, never bound to any star at all. The unusual chemistry of 3I Atlas, especially its volatile ratios, has inspired a few researchers to consider this possibility. Its CO₂ dominance could reflect condensation within a deeply cold region of a molecular cloud beyond the reach of radiation from any young star. If true, then 3I Atlas was not simply alien to our solar system, it was alien to solar systems themselves. It would be a relic of pre-stellar chemistry, a shard from the time before stars condensed a piece of the galaxy's raw molecular architecture. This interpretation, though speculative, had a poetic resonance. 3I Atlas as an object older than starlight. 4. The Oumuamua question and its lessons. Every interstellar object now exists in the shadow of Oumuamua, whose shape, tumbling motion, and non-gravitational acceleration provoked spirited debate even among the scientific community. Though consensus now holds Oumuamua's natural, its unusual nature opened the door to broader speculation. Naturally, some asked, was 3I Atlas another anomaly, another aberration, another puzzle hinting at deliberate construction? The answer drawn from extremely thorough analysis: no. 3I Atlas behaved as comets behave. Its mass loss patterns matched natural sublimation. Its acceleration matched physical models of outgassing. Its dust composition aligned with natural mineral formation. Its brightness variations lacked the rotational signature of a rigid, elongated body. Where Oumuamua had confused 3I Atlas clarified. It was unmistakably a natural fragment, but natural in a way that broadened the definition of what natural looks like across the galaxy. 5. The chemical divergence hypothesis. This was perhaps the most intellectually provocative model. In this interpretation, 3I Atlas was not remarkable because it was unusual. It was remarkable because it was typical for its own stellar birthplace, meaning the solar system may be chemically provincial. We may not be the average, we may be the outlier. If comets from other systems commonly contain much higher CO2 than ours, if their dust forms at different temperatures, if their metallic ratios vary widely, then the galaxy's diversity of chemical environments is far more intricate than our limited sample of one system suggests. This interpretation reframed 3C Satellis not as a curiosity but as the first data point in a vast uncharted distribution. A reminder that planetary systems across the galaxy are not siblings, they are strangers. 6. The deep time perspective. Every interpretation, no matter how grounded or bold, shared one unifying theme time. Not human time, not even geological time, but galactic time measured in hundreds of millions of years in the slow churn of spiral arms, in the quiet drift of stars around the Milky Way's core. In this temporal scale, 3 Atlas was not an anomaly. It was ordinary, merely one of countless objects freed from their systems during the galaxy's great migrations. What made it extraordinary was not its nature. It was that it crossed paths with us during the short fraction of cosmic history in which humans could observe it. 7. A new category: extrasolar witnesses. Some researchers proposed a conceptual category that blends all interpretations. 3I Atlas is an extrasolar witness, not a messenger by design, not a probe by intention, but a witness to the rise and fall of stars, to their planetary architectures, to the quiet violence of cosmic evolution. Under this view, 3I Atlas represented the simplest and most profound truth: the galaxy is old, diverse, and filled with the remnants of countless worlds, interpreting without fantasizing. In the public imagination, mysteries often demand sensational explanations. But in science, in the disciplined contemplation of the universe, the greatest revelations are often the most grounded. The interpretations surrounding 3I Atlas did not require breaking physics, they only required widening it. To consider that planet formation does not follow a single template. To accept that stars older than ours birthed worlds whose chemistry we are only now beginning to glimpse. To imagine planetary systems dissolving into dust millions of years before Earth existed. To recognize that the galaxy is more diverse than our solar system's story alone can tell. What 3I Atlas ultimately represents? It represents possibility, not the possibility of life, nor the possibility of threat, but the possibility of knowing, of understanding the Milky Way not from afar, but through the rare physical samples that drift into our cosmic yard. Each interpretation, conservative or bold, shared a final revelation. The mystery of 3I Atlas was not about what it could be. It was about what it allowed us to imagine, and what it taught us about how little we have yet seen. As 3I Atlas arced past perihelion and began its outward climb toward the distant planets, scientists confronted a sobering truth: they had only one chance to study this interstellar visitor up close. It would never loop back for a second orbit, never again drift inside the sun's embrace, never again offer the clarity of sunlight illuminating its ancient surface. This was not a periodic visitor, but a transient phenomenon, a traveller whose brief presence demanded relentless observation, coordination and ingenuity. Thus began the phase of ongoing testing, a scientific pursuit shaped not by leisurely curiosity, but by urgency. Every observatory, every spacecraft, every instrument still capable of seeing the object was called upon one after another, as though the entire solar system had become a vast distributed laboratory. James Webb, the long goodbye. Among all the instruments humanity possessed, the James Webb Space Telescope held the most enduring role. Its capacity to observe faint objects in deep darkness made it uniquely suited to track 3I Atlas, long after other telescopes lost sight. Where Hubble would eventually be blinded by distance, Webb would continue gathering chemical signatures, even as the comet retreated past Jupiter-Saturn and eventually Uranus. This work was subtle spectroscopy rather than imaging. Webb's mission was to monitor changes, how the carbon dioxide outgassing evolved as the comet cooled, how water sublimation tapered off, how dust grain signatures shifted as production slowed, whether any late-stage volatile species emerged from deeper layers. Every fading line in the infrared spectrum told scientists something about the internal architecture of the nucleus. A declining CO2 signature, for instance, might suggest that the comet's surface layer was unusually thin, exposing deeper layers earlier than expected. A delayed release of water might reveal a crystalline structure hardened over billions of years. And any unexpected organic signatures could hint at interstellar chemistry beyond what radio astronomers have detected in molecular clouds. Webb would be in effect the comet's final companion, its last witness, as it dimmed into the vast dark. Ground-based telescopes, the last images. while Webb-tracked chemistry ground-based facilities would pursue optical and near-infrared imaging as long as physics allowed. The Vera-Rubin Observatory, though not yet fully operational during the comet's closest approach, was expected to pick up the object on its outbound escape. Rubin's immense 8.4-meter mirror and rapid sky survey cadence promised to track the fading of the coma with unprecedented precision. The decline in brightness would map the last vestiges of sublimation, offering one final dataset to constrain the nucleus size and shape. Meanwhile, instruments like the Keck Observatory, the Large Binocular Telescope, and the European Southern Observatory would conduct episodic spectroscopic snapshots, building a timeline of gas evolution over months and years. As the comet crossed 5 astronomical units, then 10, then 20, these telescopes would gradually bow out. Their limits were not technological but physical. Light dims, contrast falls, noise rises. Eventually the comet would become just another faint point swallowed by the distance. Spacecraft beyond Mars, a distributed array. Other spacecraft some decades old would take up roles in the extended watch. Lucy, bound for the Trojan asteroids, would capture periodic frames as long as its cameras could resolve the comet above background noise. Even faint detections would help triangulate the trajectory with greater precision, reducing uncertainties in the comet's exact path through interstellar space. Psyche on its deep space cruise would have similar opportunities. Both spacecraft would likely capture 3 satellites at vast distances where the coma had collapsed and only the nucleus remained active or perhaps even frozen. WISE, NEO-WISE. Though aging could provide mid-infrared detections that would characterize the cooling rates of the dust grains shed earlier in the comet's journey. These dust grains drifting in the solar wind might reveal size distributions too subtle for direct imaging. Radio observatories listening for the echoes. Several radio arrays across Earth, the Atacama Large Millimeter Submillimeter Array, ALMA, the Very Large Array VLA, and the IRAM facilities planned to scour the sky for the radio whisper of residual gases long after visible light instruments fell silent. These telescopes could detect lingering CO rotational lines, faint signatures of methane or carbon monoxide, the thermal glow of dust particles cooling at great distance. These detections, if successful, would help determine how quickly the comet shed heat information linked to its density, porosity, and internal structure. ALMA, with its astonishing sensitivity, was particularly well suited to detect exotic molecules, often found in molecular clouds but rarely abundant in solar system comets. If such molecules appeared around 3 Atlas, they could reveal even deeper insight into its primordial chemistry, trajectory refinement charting its return to the void. As the object drifted outward, the Jet Propulsion Laboratory and the European Space Agency would continue updating its trajectory, narrowing the uncertainties in its outbound vector. These refinements matter profoundly. Once 3 Atlas leaves the solar system, the smallest gravitational uncertainties combined with stellar perturbations over millions of years will blur its future path into a haze of probabilistic outcomes. But while still within range of spacecraft, the object's exact direction could be pinned down with enough precision to identify, at least in broad terms, the stellar environment it will pass through next. This would not answer the question of origin, but it might illuminate the question of destiny. The unasked question, should we chase it? A few voices within the scientific community quietly but earnestly began proposing something once considered science fiction. A probe, launched not just to study a comet but to pursue an interstellar object itself. The concept was simple in premise, impossible in practice, yet no longer unthinkable. A spacecraft designed for extreme speed could, if launched within the next decade, potentially intercept 3 Atlas somewhere between the orbits of Uranus and Neptune. There, in the cold periphery of the solar system, the probe could image the nucleus, directly sample dust streams, and detect chemical signatures unreachable from Earth. Such a mission would require propulsion far beyond current technology, solar electric drives, nuclear thermal engines, or even solar sails, but the scientific reward would be incomparable. 3. Atlas, in its quiet flight outward, raised a provocative question. Should humanity chase the things that drift into our sky? Should we seize the chance to study a world older than Earth up close? The Long Watch. As 3 Atlas moves outward toward the orbit of Jupiter in early 2026, then towards Saturn, Uranus, Neptune, and beyond the solar system's fleet of instruments will continue their vigil. Webb will listen for the fading echoes of ancient chemistry. Rubin will track the dimming coma. Alma will search for the radio ghosts of long-frozen volatiles. Lucy and Psyche will capture distant glimmers to refine trajectory. The Deep Space Network will gather telemetry from every craft still able to see. Eventually, one by one, each instrument will fall silent, not because the object is gone, but because its light has dissolved into the cosmic background. But the observations collected from Hubble's early images to MAVEN's ultraviolet signatures, from Webb's chemical readings to SOHO's backlit silhouettes will remain. A dataset so rich, so unprecedented, that astronomers will spend decades mining it for meaning. For in studying 3I Atlas, humanity is not merely observing an object, it is learning how to observe the galaxy itself. Interstellar visitors will come again, some sooner, some later, some perhaps already crossing the outer heliosphere even now. And when they do, the methods forged through the study of 3 from Atlas, the cross-solar system coordination, the rapid spectral response, the multi-vantage geometry will stand ready. A new discipline has quietly emerged into stellar object science, a field defined not by theory alone, but by opportunity. And 3I Atlas was its turning point, its catalyst, its first true case study in the era of telescopes and probes capable of catching a relic from another star at last. The science is not finished. The pursuit is only beginning. As 3I Atlas continued its outward drift, its coma collapsing, its glow fading, its ancient gases freezing once more into silence, the scientific pursuit slowly gave way to something deeper. The interstellar visitor had revealed its chemistry, its dust, its trajectory, its volatile structure, and even faint hints of its long-dead birthplace. But now, as it crossed beyond the reach of routine observation, a final question rose, not one of science alone, but of meaning. For what does it signify when a fragment older than Earth enters our sky for a moment, revealing only glimpses of its story before returning to the cosmic dark? What does it mean when a worldless wanderer passes beneath the warmth of our sun, illuminating truths we did not know to ask? 3I Atlas in its passing became a mirror not reflecting our planet, but reflecting our place within the galaxy. A messenger without intent. To call it a messenger is metaphor, not physics. The comet carried no message, no purpose, no destination. It did not choose its path nor aim for our system. It drifted according to laws so ancient that they barely resemble decision. And yet, by encountering us, by letting our sun ignite its frozen ices, it spoke more eloquently than any deliberate envoy could. Its chemistry told us that planetary systems form in ways more diverse than our models suggest. Its dust whispered of stellar nurseries colder than anything our sun has known. Its volatile ratios reflected the fingerprint of a star older than our oceans. Its motion traced the memory of a galaxy where stars wander and dissolve over billions of years. 3I Atlas did not bring meaning. It revealed that meaning is something humans weave from the quiet facts of nature. The fate of forgotten worlds. In every interpretation of its origin, one theme returned like a gravitational constant. The comet belonged to a system that may no longer exist. Perhaps its parent star dimmed into a white dwarf. Perhaps its planets were torn apart by migration or collision. Perhaps the system simply aged into dust, its memory erased except for the few fragments cast out into the galaxy long ago. To witness 3I Atlas was to confront the impermanence of worlds. If an interstellar comet can survive billions of years after its sun has vanished, then what of Earth? What fragments of our world will drift through the galaxy in unimaginable epochs? Will any carry clues of our oceans, our mountains, our biology, our brief rise into awareness? Or will the only memory of our system be rocks stripped bare of context, their stories indecipherable to whatever future intelligence encounters them? 3I Atlas reminded us that every world is temporary, but the dust of worlds endures, a shard of deep time. When scientists spoke of the comet as older than the sun, they were not speaking poetically. They meant it literally. Its elements condensed in a time when the galaxy was younger, when the spiral arms had not yet settled, when the cosmic environment contained fewer metals, fewer complex molecules, and fewer warm places for planets to form. To study 3I Atlas was to look backward along the arrow of time, back to an epoch inaccessible to telescopes, unrecorded even in the oldest rocks on Earth. In its drifting nucleus, the comet carried the temperature profile of a primordial nebula, the dust chemistry of an ancient star-forming region, the volatile distribution of a world shaped before our own, the quiet scars of cosmic rays accumulated during endless wandering. It was not a relic of our history, but of the galaxy's. And in studying such an object, humanity glimpsed its own position within a continuum of time far larger than civilization itself. The quiet humility of cosmic perspective. Astronomy often confronts us with scale distances so vast they erase intuition, times so long they dissolve certainty. But 3I Atlas offered something subtler perspective. It reminded us that mystery does not need to contradict physics to be profound, that the universe is not strange because it is impossible, but because it is greater than our lived experience. In a world often consumed by immediacy, the comet slowed thought, deepened reflection, and expanded imagination. It asked nothing, it demanded nothing. It simply passed through our sky, offering its story to anyone willing to listen. A universe of stories we have yet to hear. 3I Atlas was the third interstellar object ever observed. But statistically, thousands pass through the solar system each year, most too faint, too small, or too distant to detect. If even a handful resemble 3I Atlas in their chemistry and structure, then the galaxy contains an immense archive of worlds, long-gone fragments drifting silently between the stars, each carrying a different chapter of cosmic history. We are only now learning how to listen. As telescopes grow more sensitive, as missions grow more ambitious, as spectroscopy becomes more exquisite. Future interstellar travelers may reveal even stranger origins, deeper chemistries, more complex pasts. Some may come from systems still vibrant, others from systems newly formed, others still from violent regions sculpted by supernovae. And someday, perhaps decades, perhaps centuries from now, humanity may launch a mission capable of catching one. Not merely observing it at a distance, but approaching it, photographing its nucleus, directly sampling its dust, and holding in our instruments a piece of another star's history. 3I Atlas then becomes not an ending but a beginning, a reminder that the galaxy is not a distant abstraction but a living environment through which remnants drift, carrying the memories of ancient fire and frozen time. The light that fades, and so the comet recedes. Its coma collapses inward like a closing flower, its jets quiet, its tail thins into invisibility, its nucleus becomes once more a cold, silent stone. Soon not even Webb will be able to hear its molecular whispers. Soon only trajectory models will trace its motion. Soon it will return to the interstellar dark from which it came. But something remains. Not in the sky, in us. 3 Atlas changed nothing about the universe, but it changed our understanding of it, enlarging it, complicating it, enriching it. Its passing leaves behind not loss but clarity, that we live in a galaxy filled with forgotten worlds, that the remnants of those worlds sometimes wander close enough to see, and that to witness them is to glimpse not merely the past, but the vastness of what remains undiscovered. And now, as the final traces of the comet fade from view, the pace of the story gently slows. The bright rush of discovery softens into reflection, and the sharp details dissolve into a quieter landscape of thought. Beyond the orbit of Mars, the interstellar traveller dims into the stillness of deep space, its light becoming thinner, its voice becoming fainter, until it merges once more with the long silence between stars. Imagine it now, a small ancient fragment drifting through the night, carrying the memory of a vanished sun. No engines, no purpose, only the patient companionship of the Milky Way's endless dark. Its path stretches onward for millions of years, a trajectory shaped by gravity and chance, untouched by intention. And somewhere far ahead, in a future long after the lights of our cities have faded, it will slip past another star unseen, unnoticed, continuing a journey older than human language. The observations end, but the wonder does not. What remains is the sense of scale, the sense of time, the sense of quiet awe that rises whenever the universe reveals something rare and delicate. The world returns to its familiar rhythms, yet above it all in the vast sky we barely understand fragments of forgotten worlds continue drifting, waiting to be illuminated by the next sun they pass. So rest now beneath the same stars through which the comet travelled. Let the story soften, let the cosmic distances widen into comfort, let the universe feel vast but gentle for a moment. The mystery of 3I Atlas does not vanish, it simply becomes part of the long, slow tapestry of the sky. Sweet dreams.